Fourier analysis is to represent signal in frequency domain. We want to obtain the frequency distribution for the signal in frequency domain. Such distribution of the frequency component is called spectrum. When we talk about spectrum, by default, we talk about frequency domain. So therefore, spectrum and frequency domain, they refer the same thing. Signals can be represented in time domain or frequency domain. So both ways now. Thinking about our hands have two sides, upper side, the front side, and the back side. When we look at our hands, we can look at on the front side. We can also look at the back of our hands. Considering both sides, we are just look at our hands. So the same thing as signals. If we look at the signals in time domain, and also that's we look at time domain, we look at the waveform, or how the waveform been changing with time. But signal can also represented in frequency domain. So the signals can be represented in both domains. The connection between these two domains, that is Fourier transform. In communication systems, sometimes it's very convenient and meaningful to look at signals in time domain, and sometimes it's more meaningful to look at signals in frequency domain. It depends on the situation. Let's look at an example here. If I have a system, I draw here. Okay, so this is a linear time invariant system. Impulse response is h of t. The input is x of t. The output is y of t. You see, when we talk about the system, the input is two-dimension functions. It's a function of time and also it's a function of value. The output is a function of time, it's also a value. Output y of t is the convolution of, this is a star convolution of this two signals together, the input and the impulse response. And this we learned in the prereq. So for example, if the input is a sinc function, and let's assume that the impulse response, that's a sinc function as well, then this is a two sinc function convolute together. So if x of t equals to h of t equals to sinc t. So this is basically two sinc functions convolute together. But to calculate the convolution in time, you need to do the integral from minus infinity to infinity, and h of tau and x of t minus tau, and then you do the integral with respect to tau, and then you obtain the function of time, that's y of t. But this is the integral, is not easy to do the integral in time. Convolution in time, that's basically the product in frequency domain. So y of f equals to x of y, so multiply product h of f. So convolution in time become the product in frequency domain. In the calculation perspective, the integral is normally harder to evaluate than direct product, right? So if we take this example, there's a sinc function. Sinc function has the frequency domain spectrum as a rectangular, and this is rectangular. So this is another rectangular, right? So these two rectangular multiply together, it become another rectangular. And then take inverse Fourier transform, we can obtain the output in the time domain. So this way is much easier to calculate the frequency domain first. And one thing to remember about Fourier transform or Fourier representation of signal is that in frequency domain, we are dealing with complex functions. When we talk about a complex function, we have real part function, we have imaginary part function. Or we talk about magnitude and phase, and these are all functions of frequency. Let's look at the Fourier transform. The time domain function is x of t, that's a small x, and time, the variable is time t. And then in frequency domain, we use a big X, capitalized. The argument is f, that's frequency in hertz. These are a pair. One, the same signal, one is in frequency domain, the other one is in time domain. So the definition of Fourier transform from the time domain is this. We take the time domain function, multiply by the complex exponential e to the power minus j 2 pi of t, and then we do integral with respect to t from minus infinity to infinity from the whole real line. So the function after the integral is a function of f because the variable t has been integral out. And then we can, using this notation as xf equals the Fourier transform square bracket xt. So f here, curly f, is operation. It's operation by doing this. The inverse Fourier transform is to transform from the frequency domain back into the time domain. So we know the Fourier transform is xf. We multiply by the complex exponential of e to the power j 2 pi ft, and we do integral on f, the frequency, from minus infinity to infinity. We obtain the function of time, that is x of t. Then in notation wise here, ext can be written as inverse Fourier transform. This is called inverse Fourier transform. The argument is xf. This is square bracket. F, curly f, is a Fourier transform, and at curly f inverse, that's inverse Fourier transform. That's both are operations. This curly f and curly f minus are both operations. EXF is called the spectrum of ext. That's a Fourier transform of xt. We can see it's normally complex because the complex exponential here involved, the spectrum will be complex. We need to using the magnitude and phase to express, to represent the frequency domain. So we use magnitude, xf, and the angle of xf to represent the whole picture of the frequency domain component or the spectrum. Not only the Fourier transform is complex functions, but also it contains positive frequency and negative frequency. That is in theory when we calculate the Fourier transform. And notice that in real systems, there is no negative frequency, but why in theory we need to have negative frequency. And here is why. Positive frequency corresponding to e to the power j omega t, that's a complex exponential. The phasor rotates counterclockwise like this way here. A negative frequency corresponding to the term of e to the power minus j omega t. The phasor rotates clockwise here. We need both this frequency, positive frequency and negative frequency, when they sum together, we can obtain cosine omega t. This is a real signal. And this real signal, that's a signal we have in real systems. And this can be justified by using Euler's formula. J omega t equals to cosine omega t plus j sine omega t, right? And then e to the power minus j omega t equals to cosine omega t. There's a bracket here and bracket here just in case. That will be minus j sine omega t. Right? And then if we sum them up, we will have 2 cosine omega t equals e to the power j omega t plus minus j. Right, so if we have positive frequency and negative frequency and sum them up, we're going to have real signals. And this is the signals in real system. But in theory, we need to have the negative frequency. Now we use some frequently used Fourier transform pairs. First is delta t. The Fourier transform is 1 in frequency domain. What does it look like in frequency domain? It will be like this. So this is the F. Frequency domain is all 1. Magnitude all 1. It's here. What does this mean? This means that this signal occupies the whole frequency span from minus infinity to infinity. We know that in time domain, we know it's not possible for a real system to generate a signal with infinite magnitude in time. We can also justify it in frequency domain. There's no such system that they occupy the whole frequency span from in real system from 0 DC to infinite frequency. So in this way, we can see this signal is imaginary. It cannot be realized in real system, but delta function provide a lot of convenience in analyzing the signals for real system. This delta function is a tool mathematically to make our analysis easier. Now let's justify this. And also I use this example to illustrate the delta function properties. Let's take Fourier transform of delta. So Fourier transform of delta t, you do by definition. We do integral delta t e to the power minus j 2 pi ft. You do integral with respect to t. Now let's brought up the property of delta function. So now this is a property of delta function that extracting the function values at t naught. So we take integral from minus infinity to infinity, phi of t, that's any function, and multiply by delta t minus t naught and do the integral. If we look at this and this is a special case when t naught equals to 0. Right? So using this property, we're going to have e to the power minus j 2 pi f multiplied by 0. What is equals to? That equals to 1. Another typical Fourier transform pair is pi of t. Rectangular in time, corresponding to the sinc function in frequency domain. The other one is a sine t, which is the indicator. The frequency domain is 1 minus j pi f. Another Fourier transform pair is complex exponential e to the power minus j 2 pi f naught and t. In frequency domain, that's a pulse, impulse in frequency domain. That's a delta f minus nf naught. So here nf naught, n is known, f naught is known. In frequency domain, that's a delta function. Now we can look at a very good property of Fourier transform. When the time domain signal is real, then xf, the Fourier transform, or the spectrum, is Hermitian. What Hermitian means that if I flip the frequency domain of the spectrum, that's x minus f, that equals to I take the conjugate of the Fourier transform. This property, if we transfer to the angle and magnitude, it means that the magnitude is symmetric along the y-axis, and the angle is anti-symmetric because of this negative sign here. We can look at this property. Pi of t, that's a real signal. The frequency domain is sinc. We can see here, if we take magnitude of sinc, we take absolute value, the sinc function, the magnitude are all symmetric. And let's look at this. Delta t, that's real. What is the Fourier transform? That's 1. It has a symmetry for x minus f if we take magnitude, and xf for sure because of the special case. The spectrum is also 1.